Hi, I'm Anurag Sarkar, and in this presentation, I'll be talking about tile-to-tile, which is an approach that we introduced in this work for performing a form of style transfer between levels of tile-based platformer games. This approach is enabled by models that we refer to as filters, which are trained to translate levels from sort of a game-agnostic representation based on affordances into a game-specific tile-based representation. And we'll see in the rest of this talk how the ability to do this enables this type of style transfer between games. But first, to motivate this, in recent years, we've seen PCGML work, such as the ones shown on this slide. So work about generating new games by recombining graphical representations of existing games, blending games by blending their latent representations, learning tile embeddings across a set of games, as well as work performing domain adaptation. All these works, they differ from sort of a more traditional application of ML for PCG in that rather than learn distributions of individual games, these types of work focus on learning and reasoning about design spaces spanning a number of games, and thinking about applications beyond just generating levels for one particular game. And along these lines, a potential application we can think of that hasn't really been explicitly attempted, at least not how we present it here, is that of video game style transfer. Now, neural style transfer was introduced around 2015 and has since become a really well-known application of ML, specifically within the visual art domain and a well-known application of creative ML in general. Initially, it was introduced as a way of transferring style from one image to another, but then the pix-to-pix model was introduced a couple of years later, which learned to translate not just between individual images, but sets of images. And so it enabled this form of style transfer between different image domains rather than individual images. And this pix-to-pix model is one of our primary motivations as reflected in the name of our approach. But overall, this notion of style transfer remains fairly underexplored within the games domain. There have been some pixel-based approaches that just swap out the visuals of a game with that of another game or a city landscape, for example, but none to our knowledge that address sort of the functional aspect of the game levels that are being translated. Additionally, a lot of PCGML works have benefited from precise, discretized tile-based representations of levels, such as those we can find in the VGLC, and so we were interested in developing a style transfer method for games that worked with tile-based representations. And so we introduced this style transfer approach called tile-to-tile, which at a high level consists of a two-step method where we first convert the level from the source game A to a low-resolution affordance-based representation common to both the source and the target games. We call this representation a sketch, and then we translate that sketch into the game-specific tiles for the target game B using a trained model, which we refer to as a filter. Again, this is conceptually similar to the pix-to-pix framework, only here, instead of training models for translating between sets of images, we translate between sets of tile-based levels. And so central to this approach is the concept of tile affordances, and the affordances of an object or tile refer to the valid in-game interactions and actions that it permits. The key idea behind this approach is that while games differ in their specific external tile-based representations, they often share underlying affordances. So as an example, Mario has Goombas, whereas Metroid has its Metroid creatures, but they can both be considered as enemy characters. In this work, we used 4 games, Super Mario Bros., Kid Icarus, Mega Man, and Metroid, with the levels all taken from the VGLC. And for each game, we defined a mapping from its original tiles to a set of affordances shared across all 4 games. And then we train a model for each game to convert from the affordances to that game's tiles. We use 2 types of models in this work to act as the filters in the tile-to-tile framework, namely Markov random fields and convolutional autoencoders, and I'll discuss these next. So first we have the Markov random field, or MRF, and these learn conditional probability distributions for a particular state given its surrounding states. And here we can use MRF since for the task of style transfer, we already have a source level to begin with, and thus have a set of surrounding tiles for each position, unlike when generating levels from scratch where typically we would only have the preceding tiles. And so using an MRF allows us to consider a given tile's dependencies in all directions. Now, in the tile-to-tile framework, the role of the model for a given game is to learn to map affordance tiles to tiles specific to that game. And using an MRF, we model this as learning the probability of a location being a certain game-specific tile, given the affordances of the surrounding neighborhood of that same location. And so the surrounding neighborhood can be thought of as the context for the specific central tile. In other words, the MRF for a game learns the probability of tile occurrences given a surrounding affordance context. We tested two contexts in this work, one looking at the four affordance tiles north, south, east, and west of the central tile, and the other looking at the full 8 tile surrounding context, as shown in the picture on the slide. And more details regarding the training process of the MRF is given in the paper, but just at a high level. The MRFs were implemented as dictionaries with each unique context serving as a key, and each key mapping to the distribution of center tiles for that context. To train the MRFs for a given game, we first convert each level to its affordance form using that game's predefined tile to affordance mapping. Then we slide a 3x3 window across each level, updating the counts of the original center tiles for each context that we find along the way. And so after this step, the dictionary stores the number of times each original game tile appears in the center for each unique affordance context. In the final step, we just convert each context's absolute counts into a distribution that we can sample from when performing style transfer. Moving on to the autoencoder, so for each game we train convolutional autoencoders using 15 by 16 segments from that game. For training, for each game we collected pairs of level segments consisting of the original segment along with its sketch version obtained by translating the original segment using the tile to affordance mapping for that game. And we used the sketch as the encoder input and computed the reconstruction error between the resulting decoder output and the original segment. So training in this way, the autoencoder for a given game learns to convert from the common affordance representation to the tile specific to that game. And this type of training is similar to denoising autoencoders, where instead of using a noisy, corrupted version of the data as input, here we use this translated version of the original input. And so then how do we do style transfer using these models? Well, the first step is the same for both. We convert the level from the source game A to the affordance-based sketch representation using the predefined tile to affordance mapping. And this is done manually since this mapping is deterministic. And in the second step, we apply either the target game's MRF or autoencoder on the converted level. So in the case of the MRF, the Markov random field, we slide the 3x3 window across the source level, converting the center tile as we move along. And in the case of the autoencoder, we forward 15 by 16 segments of the level through the target game's autoencoder. And just to touch upon a couple of differences between the two models, the first being that the MRF, by design, by the way it works, it keeps the underlying affordances fixed while translating the higher level game-specific tiles, whereas the autoencoder has to generate this underlying content, the underlying affordances from scratch. And second, the second difference is the granularity at which style transfer is performed. So the MRF performs style transfer tile by tile, whereas the autoencoder does this segment by segment. And here we have a couple of examples of what this style transfer actually looks like. So these are a few examples obtained using the Markov random field. On the left, we have a Mario level translated to Kid Icarus, and on the right, we have a Mega Man level translated to Metroid. And these are some examples using the autoencoders. And a qualitative difference worth mentioning is that since these autoencoders work at the segment level, the output levels are less noisy than the ones produced by the Markov random fields because they convert each level one tile at a time. But then for that reason, because the MRF works one tile at a time, you can use it to style transfer any custom amount of the level and not be restricted with these fixed size units or segments of levels as in the autoencoder. And before moving on to the evaluations, I do want to point out something that's fairly important to this work and informs our evaluations, and that's this notion of affordances and tiles can be considered as analogous to the style transfer concepts of content and style, where content refers to the underlying structures and objects in an image, while style refers to the high-level visual characteristics such as color, paint style, textures, and so forth. Similarly, we can consider affordances as representing the underlying game-agnostic structures and topologies such as generic solid tiles and collectibles, and the tiles as representing the high-level game-specific appearance. So using this analogy, the goal for us is to keep the underlying affordances similar while translating the high-level game-specific tiles. And as I mentioned, this served as sort of the basis for our evaluations. And so with that in mind, we performed a three-part evaluation, separately looking at these notions of content and style, and also performing a third evaluation to get a sense of how playable the style transfer levels are. So first we evaluated content, and again, we want the underlying affordances related to the level topology and structures of the target levels to be close to the source levels while transferring the style of the higher level tile representations. And so to evaluate that, we introduce this affordance pattern KL divergence metric with which we compare the tile affordance patterns in the input source and output target levels. This metric is the same as the tile pattern KL divergence metric introduced by Lucas and Waltz that has come to be fairly widely used in PCGML research, the only difference being that we use affordance tiles when computing the metric rather than the original game tiles. And in computing this difference in affordance patterns between the source and target levels, this APKL div metric can be viewed as being analogous to the content loss from visual art style transfer. I do want to clarify, however, that for MRF, since the style transfer process keeps the affordances fixed from source to target, this evaluation would not really be useful. So we ran this evaluation only for autoencoders, and in that case, it is very useful because the autoencoders have to generate the affordances from scratch and learn to keep the affordances in the target the same as in the source. And then to perform this evaluation for every pair of source and target games S and T, we consider three sets of level segments. The first we refer to as OG source, so these are the original segments of source game S. Then we have the TF target set, which consists of the segments obtained by applying the autoencoder for the target game T on the original segments of S. And we computed the APKL div value between these two sets using their affordance-based representations. And we also consider a third set of segments, which we call OG target, which is just the original segments of the target game T. We also computed the APKL div between the TF target and OG target sets of segments. And for effective style transfer, we would expect the equation shown on this slide to hold true. And to understand why, consider the example of a style transfer from Mario to Kid Icarus. In that case, we would expect that the underlying affordances or content of the style transferred levels to be closer to Mario-like affordances than Icarus-like affordances. Since we are style transferring from Mario to Icarus in this case, we would want the underlying Mario-like content to be preserved. And in case that's not very clear, I encourage you to look up the paper where this is explained in more detail. But our results for this evaluation were true to expectation, as shown in the slide, where for all pairs of games, the APKL div between the style transfer target levels and the original source levels were lower than that between the style transfer target levels and the original target levels. And so the takeaway here is that the autoencoder is able to preserve the underlying content of a level when performing style transfer. And so moving on to the style evaluation, so here we consider a game's specific style to be defined by the tile representation or tile histogram of its underlying affordance patterns. And to evaluate this, again, for each pair of games, source S and target T, we computed the tile histogram of the levels obtained after performing style transfer with the original tile histogram of the target game T. So here we have the results. So this figure is showing the tile distribution of each of the original games on the left. In the middle, we have the tile distributions obtained via style transfer using the Markov random field, and on the right, the same, but using the autoencoder. And we see that in all cases, the tile histograms for the games after style transfer are very similar to the original tile distribution for each game. Now, we do not expect these to be identical since some amount of difference is expected when trying to match affordances between source and target, but they are very similar. And so the takeaway in this case is that the style transfer levels do have similar tile distributions as the original target levels. Finally, we evaluated the playability of style transferred levels. Now, even though the Markov random fields can work with levels of arbitrary size, since autoencoders can only work with fixed size segments, for an even comparison, we evaluated the playability of both models with segments. And for this evaluation, for each source target game pair, we computed the percentage of segments that were playable by the target game's A star agent after performing style transfer using the target game's model. And the results are shown on this slide. So some general takeaways are that performance varies quite heavily for different pairs of games. And overall, we do obtain fairly high playability percentages for several pairs, but it is quite reasonable that there would be a dip in playability after transferring style. And perhaps in the future, we could look into ways in which we can repair some of these style transfer levels to ensure that a level remains playable after performing style transfer. And so to conclude with a few future work possibilities, we do wish to validate this approach further with user studies and also develop an application for users to be able to apply the trained filters to perform style transfer on either pre-existing or hand-authored levels. Additionally, we could use style transfer to supplement training data for games that don't have sufficient data to train on. And as with much of our prior platformer-based work, we would like to generalize the method to work with games of other genres. And that brings me to the end of this talk. Thank you.